Hi everyone, it is Mrs. Smeagol and I have a video to get us started today, and then you're going to watch some videos on your own. I'm recording this on a Sunday. The Bears have their first victory of the year. Woo! Sitting in the Lego room at my house, as you can see. We like lots of Lego. That's the Harry Potter wall, but there's some other fun surprises if you really look. Okay, so here's the plan. You guys are going to watch this video, and we're going to fill out the top of your nuclear fission and fusion and fission page. The first half we're going to do together in this video, and then when you turn it over to the back, you're going to watch 3 videos on your own. Nuclear energy is terrible, nuclear energy is great. And then after that, after you watch those videos and take some notes, you're going to open up the slides, these same slides that I'm actually using to make this video, to read about some different motivations for the arguments of nuclear energy. So that's kind of the 3 steps. This video, then the 3 videos on your own, then open up the note slides for the last section. All right, so these notes are all about nuclear decay. And what nuclear decay is and why it happens is it's when it occurs because an atom becomes unstable, and that's because there's either too few neutrons to hold the protons together. Think of neutrons as like the glue of the nucleus. So if there's not enough, it won't hold the nucleus together and it'll break apart. That is what nuclear decay is. Or if there's too many neutrons, then the nucleus becomes too heavy and unstable, so it breaks apart to try to find stability. Okay, so a couple of things to keep in mind. We learned a little bit about chemical reactions at the beginning of the year. We look for like color change, odor change, temperature change, bubbling, a precipitate, things like that. Okay, those chemical reactions involve the electrons. No new elements are formed. We just rearrange the elements that are already there, and they require or use or give off small amounts of energy. Whereas nuclear reactions, what we're learning about right now, involve the protons and the neutrons, so the nucleus instead of the electrons. They form new elements and they have large amounts of energy released, and the waste products of these reactions can be hazardous. So when we have something that goes through a nuclear decay, there are 3 main types that we're going to study in this class. We're going to study alpha decay, we're going to study beta decay, and we're going to learn some about these gamma rays. Okay, there are other types of decay, but those are kind of the main ones. So let's talk about the alpha particles. If a nucleus is unstable and it releases an alpha particle is made of 2 protons and 2 neutrons. These are the same size as a helium nucleus. So they are slow, they are heavy compared to the other ones we're going to see. Okay, they're heavy, slow, and if I have an alpha decay occurring, so we have this alpha particle, it is going to be stopped by a small sheet of paper. It won't travel through the paper. Okay, that's good news for the human body, because alpha particles outside of our body won't cause damage. But these alpha particles, out of all of the different types of decay, are the most ionizing. Remember, ionizing is the dangerous type of nuclear decay. So that means if the alpha particle gets into your body, that's where it can cause damage. And we talked about that with radon in your lungs. If you have radon in your house, it can cause problems. Okay. The next type we're going to learn about is beta. And with beta, a beta particle is basically a high speed or high energy electrons. They move about 100 times faster than the big, slow alpha particles. So these guys are moving very, very, very quickly. And they can be stopped, so they can travel through a piece of paper. They're strong enough to make through the paper, okay? But they would be stopped by a thin piece of aluminum foil, or your human skin can stop the beta rays, okay? And then gamma rays, similar to X-rays, okay? Not as ionizing as the alpha particles, but a gamma ray is basically a high energy electromagnetic wave. So we looked at the picture last time of all the different kinds of waves. There was radial waves, things like that. A gamma ray is the highest energy, and they travel at the speed of light, so much faster than beta particles and alpha particles. They have no mass and no charge, but they can travel through paper, they can travel through aluminum. The only thing that stops them is lead. So if you've ever had an X-ray at the dentist, they always put a lead vest on your chest, because the lead is able to stop the gamma rays from going through your chest, through your skin, through your bone cavity, right, and hurting or doing damage inside your body. The lead is able to stop the gamma rays. And then we also have these neutron rays. These are just free neutrons. We're going to see some of those in our equations. I'll point those out to you in a second. Okay, to fill out what we're going to do with me in this video, we're going to do this page here, the nuclear fusion and fission. So you need to pull this out. If you are in A Day, you should have this from last time. If not, you can get a copy from the guest teacher, or the other teacher in the room should have a copy of this for you. So pull this paper out for me. All right, so now, let me zoom. Maybe. Okay, hopefully you can see that. So now that we know about alpha, beta, and gamma rays, we are going to talk about two categories, fusion and fission, two different categories of these nuclear reactions. So fusion and fission. With fusion, it's high, they require high heat and high pressure, and this is where two nuclei, so two different elements, their nuclei, fuse together to form one big nucleus. So if you look at the picture, this is hydrogen. It has the atomic number 1 and a mass of 2. Here's another hydrogen with the atomic number 1 and a mass of 2. And this arrow means something's happening. Think of it like an equal sign. These two are combining, that's the plus sign, adding together to create, or after the equal sign, one bigger nucleus that has two protons and a mass of 4. And that's why it's now helium, because helium has 2 protons. So if you look, the bottom of this equation here, 1 and 1, this is your equal sign, equals 2. On the top, 2 plus 2, this is your equal sign, 4. So they always add up. But a fusion is where we're bringing smaller nuclei together. Okay? When we're combining these small atoms, you're getting this larger one. Sometimes you might see some neutrons involved. I'll show you examples of that later. There is no radioactive waste typically, and we find this in the sun, our sun, and any stars in the universe. This is actually how the sun gets energy, is it fuses hydrogen into helium. Okay, the other category is fission, and in order for this to happen, you need a large unstable nucleus and high-speed neutrons. So one big unstable nucleus is going to split into 2 or more smaller nuclei. Sometimes to get this going, you need a neutron to bombard it. So here's what I have here. This is my neutron. I know it's a neutron. They use the little n for neutron, but neutrons don't have any protons. That's why there's a 0, and it has a mass of 1. So I have a neutron bombarding this big atom of uranium. And remember, this arrow is like an equal sign. So I'm really just starting with one big nuclei and then just a small neutron. That doesn't count. So that neutron bombards this big nuclei. Here's my equal sign, and it splits into 2 different atoms, and then 3 more of the neutrons are released. Okay? So that is nuclear fission. When we split larger atoms into smaller ones, it's used in nuclear power plants, and there are lots of radioactive waste materials associated. All right, let's move on to this section for models for nuclear fission. We have 2 different pictures to look at. All right, I'm going to jump to slides where I zoom in on this picture and then I zoom in on this picture. I am going to verbally talk about what the model emphasizes, what information it's lacking, and then you're going to tell me for each one how the model might be useful for you in this class, okay? And then we'll do the same for this guy. So I'm not actually going to write it down for you. You have to listen to the video to get the information for these boxes, and then you'll have to think on your own to fill out this last one. Okay. So this is an equation for nuclear fission. We already looked at this one. We have a neutron, which is not a full nucleus. It's just a single neutron bombarding a big unstable nucleus. Remember, this arrow is going to be like your equal sign. And it gives me 2 new smaller nuclei. I know they're smaller because the masses are significantly smaller than what we started with. And then it releases 3 more of those same neutrons as a result. So when we write our nuclear fission like this in the equation form, it emphasizes something important. This is called a model. This equation is a model. And this model emphasizes exactly what isotopes are produced from this nuclear reaction. So if you need to know the specific isotopes, the atomic number and the mass number of each isotope produced, having an equation like this is very helpful. But it doesn't really show us, one thing that the model is lacking, is it does not show us how long the process will last, okay? So those are the big things. It shows us the specific isotopes, but it doesn't really show us how long the process will last. It just shows us this one-time reaction. Okay? How is this model useful? I want you to decide. So look and think about how this might be helpful in our class. Think maybe about what we learned about these numbers, and you take your best educated guess about how this model could be useful for us in class. All right, so now here's a new model. It's more of a picture, okay? And you can see these little white circles here. Those are neutrons. So I have a neutron bombarding that same uranium isotope. And then we can see that it splits into the two isotopes we saw in the previous equation, the krypton and the barium, same as before. And then there's 1, 2, 3 little neutrons released. So this part so far, this first generation part, is very similar to what we saw in the equation. It's just drawn as a picture instead. But what's different is we can see that the neutrons that get released from this first generation go on to hit another atom of uranium. Because very rarely will we just have one single atom of uranium sitting. It's probably in a sample with many, many, many atoms of uranium. But the neutrons that are released in this first generation can go and bombard a new atom of uranium, and it can split into new isotopes, new elements. Okay, some of them are the same. Here's that krypton and barium again, but you can see other combinations that are possible: cesium and rubidium, xenon and strontium, things like that. And it goes on. Then the neutrons of this guy hit another uranium, and the process continues. So this shows 3 generations. This model is good at emphasizing the chain reaction nature of the fission process. Whereas the old, like the equation we just looked at, that model, that's an equation, just really showed this one generation. It did not show that this causes a next reaction and this causes a next reaction. So if you're trying to see the full chain reaction nature of the fission process, that would be a good emphasis or a good reason to use this picture. Okay. One thing that this is lacking is it still doesn't really tell us how long this process lasts, right? Does it take 100 years for it to go from the first to the second, or does it take a fraction of a second? We don't know, from first to second, from second to third. So we don't really know how long this lasts. And one thing it kind of lacks is, honestly, this is kind of a lot to look at if we just really need the simple one-step what's first happening. Okay, now it's up to you to decide how it's useful. We know it shows the chain reaction nature. We know it does not show how long this process takes, and it's kind of complex to look at. You decide how we might be able to use this or why we would like this better in class. All right, the next is the nuclear equation practice. It says fill in the missing element for the nuclear equation shown below. Identify if the reaction happening is a fission or fusion. So the first thing I want you to do is, on all of these arrows, I want you to change them to equal signs for every single arrow. There it is. Okay, so they're all equal signs. The arrow is just what we use in chemistry as like a before and an after. So this side would be like before and then after, but we're going to think of them as equals. So then I'm going to take my highlighter, and when we do these equations, the top numbers on each side have to add together. So if I look right now, on the top, on this side, we have a 4 and we have a 1. If I add together 4 and 1, that gives me 5. So I have 5 on top on this side. And that means I need to have 5 on top on this side. Right now we only have 3, so this top mass number needs to be a 2 for whatever the blank element is. Now we're going to do the same thing on the bottom. I have a 1, we need a number here, we have a 2, and then a 0 because that's a neutron. It doesn't have an atomic number or a number of protons. So then I'm going to look on my right side. We have 2 plus 0, so the bottom number here is 2. I'm just writing these little notes off to the side to help me. So that means we need 2 on this side. So if I already have 1, this bottom number needs to be a 1. It's this number, this bottom number, that tells me what element symbol I should put from the periodic table. So if I look, there's only one element that has the atomic number 1, and that is hydrogen. So in this problem, we are taking a hydrogen with 1 proton and a mass of 3, and a hydrogen with 1 proton and a mass of 2, and they are combining to make this helium nucleus with a random neutron. Okay? When we decide fusion or fission, I want you to, don't actually cross this off on yours, but I want you to not look at the neutron. So what I see here is we have two things combining to make one. We call that fusion, when we have two small nuclei combining to make one. Let's try another one. So I have this 239 has to equal my number and then 40. So I need to figure out what number plus 40 would give me 239. Okay, you can do guess and check, or you can take your calculator and do 239 minus 40, whatever works easier for you. If I do guess and check, I tried 200, and that doesn't work. 200 plus 40 would give me 240, so I'm going to do one less than that. That would be 199. Then we do the same thing for the bottom number. 94 equals my new number plus 18. And remember, we drew in the equal sign. So I need to do what number plus 18 gives me 94. Or you could do 94 minus 18. However it works in your head is fine. Just always double check. So when I do 94 minus 18, I get 76. Let's double check. Is 76 plus 18 94? Yes, it is. Now, here's the tricky part. We need to use these numbers to find the element. It's the green bottom number, the number of protons. So there's only one element on the periodic table that also has 76 protons, and that's OS, osmium. Okay? Now, here's what I see. We started with one big nucleus, and it broke into two smaller nuclei. That is called fission, when it breaks into smaller pieces. Okay? Let's try this one. 235 equals some number plus 94. If I take 235 minus 94, that will give me 141. Double check, is 94 plus 141 equal to the top number 235? Yep, I think so. Now 92 equals some number plus 36. We check 36 plus what number will give us 92, or you could think about it as 92 minus 36. That should give me 56. Double check, is 36 plus 56 equal to 92? Yep, okay. And then we look on my periodic table. The atomic number is 56. The only element that has 56 as the number of protons or the atomic number is barium, okay? On this one, it looks very similar to the first. We have one big nuclei equal to two smaller ones. So it broke apart. Think about it as like we started with a whole chocolate chip cookie, and then it broke down into a cookie and a crumb. Those are the two smaller pieces. When that happens, we call that fission. All right. Let's try this one. This one looks tricky. We have a 16 plus a 16 equals some number plus 1. Well, on this side, 16 plus 16 gives me, 32. And then that means whatever number I put here has to add to 1. So how about 31? Does that give me 32? Yep, 31 plus 1. Now my sides are equal. Now if we do the bottom numbers. Oh, goodness me. There we go. 8 plus 8 has to equal some number plus 0. So we have 16 on this side, and that has to equal 16 plus 0. Okay, that wasn't so bad. And we can always double check 8 plus 8 equals 16 plus 0. So you always have the top numbers add up and your bottom numbers add up on either side of the equals. The only element on the periodic table that has the atomic number 16 is sulfur. Okay, remember, when we decide if it's nuclear fusion or fission, we're going to ignore the neutrons, which are always the little n with the 0 and the 1. I see that we have two nuclei, the two oxygens, making one sulfur, and so that is called fusion. Okay? All right, let's do this last one together, and then I'll have you try 6 through 10. So I got my highlighter. 52 plus 4 has to equal this number here. Oh, that's the easiest one. I'm just going to add them right up in my head. 52 plus 4 is 50. Let's try that again. 56. And now we do the bottom ones. 26 plus 2 has to equal, that's going to be 28. The element that has the atomic number 28 is nickel. All right, if we look, I don't see any neutrons that we have to worry about, but I have 2 nuclei forming one bigger one. When we have 2 things making one, that is called fusion. Okay, here's what I would like you to do. I want you to pause the video, and you're going to try number 6, 7, 8, 9, and 10. When you're done at your table, I want you to check your answers with your whole table and then call over the teacher, and they will check your answers using the answer key. Okay, there are no answers in this video, so you have to pause and you have to get checked off with the teacher before you move on. All right, here's an interesting map that has the, as of 2023, all the nuclear power reactors that the United States has available and licensed to operate. So here's where we can create nuclear energy to help supply energy to the country. You can see there are none in Colorado, but there's definitely plenty, 92 of them, in the United States. This is important to know because if we are using electric power, the United States is currently divided into 3 sections, the Western, Eastern, and Texas interconnect. So essentially, these power grids have a big risk of failure and causing devastation across the country if there's major failure. For example, this actually happened pretty recently, I think, in Texas, due to their crazy heat in the summer. They had a failure in their electric power grid, causing essentially no electric power for large portions of their residents, and especially in the summer when it's hot and you don't have air conditioning or you don't have water filters that use electric power to clean your water, it can cause lots of problems. So the idea of using nuclear power could be something that's promising, because if we can move away from being on the electric power grid and shift to nuclear power, that could be something that's helpful, especially because we risk having big outages that could essentially span over half of our country. So what you're going to do now is you are going to watch 3 videos: nuclear energy is terrible, and nuclear energy is awesome. Okay, I need you to write at least 4 bullet points of notes per video. Okay, so 1, 2, 3, 4. If you have more than 4, that is totally allowed, but the minimum is 4. Okay, so for example, I know in these second and third videos, they give you 3 reasons why nuclear energy is terrible, 3 reasons why it's awesome, but I want you to also pull another fact in addition to those 3 things. Okay, so at least 4 bullet points of information per video. Okay, I do want you to finish this video though before you go and watch these 3. So you're going to watch the video, you're going to record your full 4 bullet points. Here is where you access those videos. So if you go to the agenda, video 1, video 2, and video 3, okay, and then you're also going to need the note slides for, that should say page number 2, sorry, for page number 2, which is the back side of this underneath where you record your notes. So I'll fix that by the time you get there, but you'll need the slides. So while you're opening these videos, you might as well open these slides too. All right, you'll access this video using Schoology. That's the first one. This video is also on Schoology. It's the second one. And this is the third video, also on Schoology. All right, after you finish the 3 videos, you are going to open the slides for class and scroll to where the motivations start. So it says here, in any topic, there are various dimensions to the risk-benefit that people make decisions on. It can often be helpful to identify these dimensions to grow our empathy and understand where a person is coming from when discussing a topic. So what you're going to do is you are going to look at each of the slides. There's scientific, environmental, social and cultural, and economic, all about people who are either for a nuclear power plant being added to the town of Shelbyville, or people who are against it, and their motivations fall into these dimensions or these categories. You're going to read each slide, and you're going to put a couple of bullet points about what the focus is of their argument, and then you're going to read their examples and pull a couple keywords. So like, what are some things they're saying? For example, are they using data? So it says like the experts say, or data says, like those would be some keywords. Are they speaking from their heart? Are they saying things like I believe or I feel, right? Are they using phrasing like climate change? So whatever keywords you see in the example, I want you to jot down 2 or 3 keywords. So what is their focus? You can copy that from the slide, and then don't copy their example. You're just writing down the keywords. That's your task after the 3 videos. So here's what the slides will look like. A group proposes to build a nuclear power plant in the town of Shelbyville. Many townspeople have very strong opinions on both sides. So you have your focus. This is what you can copy, the red, and then you read the yellow example and you take 3 to 4 keywords and put that in the keywords box. You'll do that for each one of these. So there's environmental, there's social and cultural, and then the last one is economic. Okay, so at this point, you should be done with this video, which means you now have to go watch the 3 videos on nuclear and take your 4 bullet point notes, and then after that, you'll go through the slides. Once you finish all of that, this whole page is done front and back. You're going to turn it into the turn-in bin for me. And then if you haven't done attempt number 3 on your subatomic particle isotope quiz, you can do that. Just a reminder, no using the internet. That's cheating, but you can use your notes and talk to classmates on your 3rd attempt. All right, thank you for working hard today while I was gone. Sorry, one last thing. If you don't finish this during the class time, I'm confused what you were working on, but it will be homework due right when you arrive next class. Bye.